So what I've got on the left-hand side of the screen here is kind of a procedure. I don't know that we have to memorize step 1, step 2, step 3. In fact, these two first steps don't have to be done in the order that I've listed them. What I'm saying is, in order for you to solve a trigonometric equation, there's two pieces of information that you really need to know. One, what is the reference angle? And two, in which quadrants can the terminal arm be in? And to find a reference angle, you use your calculator or your knowledge of the unit circle. To identify the quadrants in which the rotation angle can terminate or end, you look at the definition of the trigonometric ratio that you're using in the question. So if you had, for example, cosine of theta equals 1/2, 1/2 is a positive number. The definition of cosine is x over r is what the cosine of theta is equal to. So then you say, how can x over r be positive? Since r is always positive, the question now waters down or boils down to, where is x positive? And x is positive in quadrant 1 and 4. Over here. Right at the center of my chest is the origin. In quadrant 1, x is positive up here. Quadrant 2, x is positive here. Then once you draw the reference angle in those quadrants, then you're going to look at the sketches, and I would recommend drawing them separately. You would look at those sketches and use those sketches to determine the rotation angles. Do me a favor, please, and take a look at your work and see if you have any questions you would like me to go over. Go ahead, Ryan.
5x.
F. So we have 3 secant, pardon me, root 3 secant theta plus 2 equals 0. And I suspect that part of the issue here is this awkward domain. Okay, but let's go through the entire thing. If I have root 3 secant theta plus 2 equals 0, my first kind of step, and what I'm doing here is I'm working towards finding the reference angle. But I cannot find the reference angle until I get a single trigonometric ratio equaling a number. So I have to rearrange this for secant of theta. And that means I'm going to subtract 2 and divide by root 3. And what I'm going to get is secant of theta equals negative 2 over root 3. I'm still not really able to use my calculator to find the reference angle yet because I don't have a secant key. But I do have a cosine key. And cosine is the reciprocal of secant. So if I rewrite this in terms of cosine of theta, I just flip that trigonometric ratio over. I take the reciprocal of it. Okay? Can I ask what you did?
I got to that, but I didn't take the step. I still did the inverse of cos of 2 divided by.
And I'm guessing at that stage you got an error. Yeah. Okay. I'm going to finish this one anyway. So in my mind, so not everybody is going to be doing this because I see a lot of you going to your calculator right away to find a reference angle. In my mind, I recognize root 3 over 2 as one of those special coordinates on the unit circle. And it's negative root 3 over 2 and it's cosine, which means x. We're looking then in quadrant 3 and 4 where x is negative. And I know with the root 3 over 2, it's one of those oddball positions. By oddball, I mean not the 45-degree one, but one of the 30-60 ones. So I know it's either here or here. And I can see clearly that x here is negative 1/2. I mean, you can You can critique my drawing here and say it's not exactly negative a half, but I know that it's closer to being a half than this, which means this is the negative root 3 over 2. So in my mind, I immediately say these are the two positions, and I don't worry about a reference angle. However, there's nothing that says you can't say theta reference is the inverse cos of root 3 over 2. And I want to finish this question, even though Ryan says he's got it now, because I think it's important. You, again, hear something I said at least 2 or 3 times yesterday. If we want exact values in radians, and you take inverse cos of this number, you're going to be faced with some weird-looking decimal number. And you will not recognize what it is. So when you find the reference angle, even though we want to write it in radians, I think it's a good idea to do it in degrees. So when you put your calculator into degree mode and you take inverse cos of root 3 over 2, no negative, remember, you should get 30 degrees, am I right? So what you would then do after doing that on your calculator, you're writing a written response exam, you would say, well, theta reference is equal to pi over 6 rads. Nobody has to know how you got that. I mean, maybe a written response question on a diploma exam might ask you to explain how you got the reference angle. In which case, I think it's a legitimate explanation to say, I recognize degrees better, so I put my calculator into degree mode and took the inverse cos of root 3 over 2, and it's 30 degrees, and that's pi over 6. Or you could justify that by looking at your diagram. Anyway, I don't want to eat up too much more of our time here before we get started today, but the reference angle is pi over 6. It can be in quadrant 2, or it can be in quadrant 3. This is pi over 6. It can be in quadrant 2 or quadrant 3 because cosine was negative root 3 over 2. And the reason cosine was negative was that secant is negative. So basically, secant and cosine are negative in those two quadrants because x is negative there. Which means that if, and this is another, I'm really glad you asked about this question. This is another thing we talked about yesterday. If you have this goofy domain, which we do, negative pi to 3 pi, not everybody is capable of wrapping their head around the rotations to negative pi to 3 pi. Not everybody can do that. So ignore that and just start off by looking at these rotation angles. And then you're going to use those rotation angles to determine rotation angles between negative pi and 3 pi. This is 5 pi over 6. I'm not actually taking pi minus pi over 6. I'm just counting 1, 2, 3. 1, 2, 3, 4, 5 pi over 6. This is 1, 2, 3, 4, 5, 6, 7 pi over 6. So now what you're going to do is look from negative pi to 3 pi. Here's the difficulty, everybody. These are pi over 6s, and these are just pi's. Well, that's okay. Change this to pi over 6s. Then I can compare. I want to go from negative 6 pi over 6s up to, I guess this would be 18 pi over 6s if I multiply the top and the bottom of 3 pi by 6. So let's start with the 5 pi over 6. And really what you're focusing on here, I think, is this number. You're asking yourself if that number that I've highlighted in the rotation angle is between negative 6 and 18, because if it is, then 5 pi over 6 is in here, and it is. So we can add that to our list of solutions, 5 pi over 6. I can get to this same place by adding full revolutions to 5 pi over 6 or taking away full revolutions. So I'm going to be adding or subtracting 12 pi over 6s at a time? Because 12 over 6 is 2. 2 pi is a full revolution. So if I add 5 pi over 6s plus 12 pi over 6s, I get 17 pi over 6s. 12 plus 5 is 17. 17 pi over 6 is in here. I hope it's clear that if I add another 12 pi over 6, I will be way past this. I could take 5 pi over 6 and subtract 12 pi over 6. 5 minus 12 is negative 7, so negative 7 pi over 6. Nope, negative 7 pi over 6 is here. So this, maybe this is the way to explain it. This location leads to only 2 rotation angles in that domain. Now, so we're done with that. Now we look at 7 pi over 6. Is 7 pi over 6 in here? Well, yeah, it's between 7's between negative 6 and 18, so we also have 7 pi over 6. What if we add a full revolution? What if we take 7 pi over 6 plus 12 pi over 6? Well, 7 plus 12 is 19? 19. 19 pi over 6. No good, because the upper limit of our domain is 18 pi over 6. That didn't work. What if we take 7 pi over 6 and subtract 12 pi over 6? So $7 minus $12 is negative $5. So this would be negative 5 pi over 6. And that is in the domain. Negative 5 pi over 6 is a little bit more than negative 6 pi over 6. And if you subtract 12 pi over 6 again, you will be outside of the domain on the left side. And these are diploma-style questions. I call it a goofy domain, but it's something that you do need to know how to wrap your head around. I'll tell you what, we're going to move on because everything that we've talked about here today, you're going to get more practice, and I want to give you lots of time. I'm sorry. Go ahead, Jason. You sure? Okay. So let's spend some time talking about that because that is pretty important. So no problem getting the reference angle. What we want to do is look at the fact that in each of these quadrants, X and Y take on different characteristics. They can be positive or negative. So over here in quadrant 2, X is negative because it's to the left of the origin. Y is positive because it's above. Down here, they're both negative, and here X is positive and Y is negative. You get that, okay? So we want to use that information, of course, knowing that the first thing I've got here is X. You want to use that information along with the original, how about this? At the point where you're going to go inverse sine or inverse cos or inverse tangent, you might have, for example, cosine of theta equals negative 0.8. Okay, just as an example. And you know how to find the reference angle, and I'm just going to talk about degrees. You would put your calculator in degree mode, and the reference angle would be the inverse cosine of the 0.8. So we don't look at the negative, right? So let's figure out what that reference angle would be. And this is not going to be an exact value case because I don't think that's the nature of your question. Your question is, how do we get the second angle? How do we get 2 angles out of this? You're going to be very close to 30 degrees, but I don't know. Can you tell me? 36.86. So I'm just going to be liberal in my, did you say 36.86? So I'm just going to say 37. I'm going to be liberal in my rounding. Now, the first thing to note is that this is not necessarily one of the answers, okay? Your question is, how do you go from the reference angle to the 2 angles? And you have to now look at whether the trigonometric ratio that you were given or that you used is positive or negative, okay? Because if cosine is positive, there's two different places that can happen, but if cosine is negative, there's two different places that can happen, two other different places. Now, then what you have to do, so there's a lot here. Now what you have to do, everybody, is go to your definitions in terms of x, y, and r. And cosine of theta is always x over r, always. But if cosine of theta is x over r and this is negative, that means, and there's something mathematically, technically wrong with what I'm about to write, but it'll get the drift across to you. What that means is it's this. Okay, and all I'm saying when I put that negative in front of the x is, I'm not multiplying x by -1. I'm just saying x is a negative number. So we are looking for a place where x is negative because r is always positive. And now we go over here, and you say, well, where is x negative? X is negative well, here and here. And that means those are the two quadrants. So then when we draw this, we draw a reference angle of 37 degrees. And again, I really don't like drawing them both on the same grid. I think that can be confusing. And then we draw a reference angle of 37 degrees in this quadrant. So I'm going to pause there. Does that answer your question? Okay. Is it that you don't really have a specific question, but it's just something you have some difficulty with? Okay. Why don't I see if I can come up with some additional practice that has nothing to do with solving trigonometric equations, but it's just which two quadrants would the angle be in? And I am a firm believer in repetition leads to, we can argue whether it's understanding or just memorization, but it leads to success. Repetition leads to success. So I'm going to do that, and I'll do that for everybody, because it is a tricky thing. And by the way, we didn't even talk about secant or cosecant or cotangent. We just used cosine. So I'm going to get some extra practice stuff for you guys. Is that okay? Okay. Let's move on. We're going to be looking at what I call more complex trigonometric equations. They're more complex in the way that a quadratic equation is more complex than a linear equation. So we're going to be solving these trigonometric equations over a specific domain, like maybe 0 to 360 degrees. And then we're going to solve them over any real number. But remember that when you write your solution for a domain of all real numbers, all you do is you take your solution for one revolution and you write plus multiples of 360 or plus multiples of 2 pi. So there's not much really new here. I want to start, though, by reviewing something. I want to talk about 3 different types of quadratic equations. So this is a quadratic equation. It's set equal to 0. It has 2x squared minus 1x minus 1. And it has a quadratic term of 2x squared, a linear term of negative 1x, and a constant term of negative 1. What makes it quadratic is the 2x squared. Okay? So we could have a quadratic equation, a different example. We could have a quadratic equation of 16x squared minus 4x. And there is a quadratic term, and there is a linear term. But there's no constant term in that second equation. It's still quadratic, though. It's a quadratic equation because it contains an x squared term. We could have 3x squared minus 5 equals 0. That's a quadratic equation. It contains 3x squared, so it contains a quadratic term and a constant term, but it has no linear term. And I want to make sure that everybody's clear on how you solve these, because they're all solved in a slightly different way. Could they all be solved with the quadratic formula? Yeah, but we're not going to deal with that really. Not today. How do you solve something like this? You factor it. And I don't want to get into how we factored that. You factor it. You factor it as two binomials, and then what you do is you say that if 2x plus 1 is equal to 0, that would make the whole thing 0. Because 2x plus 1, if it's 0, you're multiplying that 0 by whatever. It doesn't matter. It will still give you 0. And the same can be said of x minus 1. So this should be very familiar to you, especially since we've done a unit on polynomial equations. Now, how is it you solve this? A lot of people think you're going to factor this thing in the same way we factor this into binomials. And it gets your brain into a little bit of a hole that you have a hard time crawling out of. You factor, but you factor out a greatest common factor. So when you see a quadratic equation that is missing a constant term, you're going to factor out the greatest common factor. Then you can set each of those factors equal to 0, right? And if 4x equals 0, then x equals 0. If 4x minus 1 equals 0, then x equals a quarter. Are you with me on that so far? So how do you solve something like this? Well, sometimes this third type of quadratic equation is factorable. But even if it is, what I'm about to show you will always work. What you do is you rearrange for x squared. I can add 5 to both sides and divide both sides by 3 and get x squared equals 5/3. And then you take the square root. So there are your two solutions. And this is really important because what's about to happen is we will have these types of quadratic equations and these types of quadratic equations and these types of quadratic equations. But they're also going to be trigonometric in addition to being quadratic. Okay. So now let's get to the official lesson. Solve these equations. 2x minus 1 equals 0. X plus 1 equals 0. Take literally 10 seconds of your time and write out the solution to these first two equations. Shouldn't be much more than 10 seconds. Did I get them right? Okay, they're solving two very basic linear equations. The first one, you add 1 to both sides and divide by 2. So this is grade, I want to say grade 10 because grade 10 is linear equations and functions, but this is, I don't know, grade 6, 7, maybe, I don't know. You can figure these out at an early age. You get to grade 11 and you're presented with this, and what your teacher teaches you is, well, you know how to factor this. And, in grade 10, your teacher might use something called the method of decomposition here, because the quadratic term has a coefficient that's not 1. I'm not a big fan of that. I know from experience that when I multiply these two binomials out, the product of this and this has to give me the 2x squared. Well, it's got to be 2x and x. I know that when I multiply out whatever the factored form is, the product of these two constant numbers has to give me the constant in the quadratic expression. So I don't worry about the negative right now. I just say it has to be 1 and 1. And then what I do is I engineer this by design so that if I did FOIL it out, I'd get 1x in the middle. So this is why I call it trial and error. 2x times x is 2x squared. Yes. I mean, I don't know that we need to check that. You put 2x and x so that you would get 2x squared. But let's see. 1 times 1 is 1. I'll leave the negative out. We do get a 1. Now, what's my inner? My inner is 1x. My outer is 2x. Can I combine 1x and 2x in a way to get positive 1x? And the answer is yes, if the 2x is negative. So then I kind of reverse engineer this. I go, well, where did the 2x come from? It came from the product of 2x and 1, which means that this has to be negative 1 and that has to be positive 1. And if you FOIL this out now, you get outer negative 2x, inner, whoops, I want positive x, don't I? I want positive x, which means that the 1x has to be negative to add to the 2x to get 1x. So when I FOIL this out, I get for my outer 2x, for my inner negative x, and that gives me what I want up top. So it's factored. I hope that you're seeing the point here. And I don't care how you factor it. Neither does a diploma exam marker. I hope you're seeing the point that once you factor this, to solve it, you've already solved it, right? All you're doing here is you're saying 2x minus 1 equals 0, and x plus 1 equals 0. So x equals 1/2, x equals -1. In other words, these two equations are subsumed inside of this. They're inside of this equation. So if you can solve this, you can solve these. And that's always going to be the case. If you have a quadratic expression, no matter how complicated it might appear at first glance, if you can factor it into two linear factors, then you change the quadratic equation to two linear equations. And linear equations are easier to solve than quadratic. That's the point of factoring. So let's solve 2 sine squared x equals 1 plus sine x. So what? 2 sine squared x. That's how it's pronounced. What 2 sine squared x means is 2 times the square of the sine of x. Okay? It's how we abbreviate it. And when it comes to your calculator, we'll talk about how you would enter something like sine squared of x. But what that basically means, and I'm going to write it out this way just for this one, is we have 2 sine of x quantity squared. We have minus 1 sine of x. And we have minus 1 equal to 0. There is this part of my brain, and it should be a part of your brain, that is saying, I see a squared on the variable, kind of, so it's quadratic. And when you solve a quadratic equation, you zero the equation. So this is my quadratic term. This is my linear term. And this is my constant term. And I got minus sine x minus 1 simply by zeroing the equation and subtracting 1 from both sides and subtracting sine x from both sides. Are you with me on that so far? Does anybody have any questions with this? So far. Okay. So this is no different mathematically than this statement. And what I'm about to write, some of you will want to write in doing your work. It's no different than me saying, well, it's a little different, but it's the same in a way as me saying, solve this equation, 2a squared minus a minus 1. And what I've done here is I've let a equal sine of x. What I've done is I've taken something that is confusing to me and I've turned it into something more familiar. And you can solve this. You factor it, you set each factor equal to 0. So let's do that. If I factor, I know that I'm going to have 2a and a. I'm using trial and error. I will never use the method of decomposition. And you know what? Usually in Math 30, these numbers that we're dealing with, I'm going to put a 1 here in front of the a. The numbers that we're dealing with are usually pretty small anyway. 1s, 2s, and 3s. This has got to be 1 and 1, and now you just have to figure out where the positive goes and where the negative goes. This time, we're going to have to put the negative with the a minus 1, I believe, because we want negative a. This quadratic is different than the one in the warm-up. Okay? The one in the warm-up had a positive there. This has a negative. I'm going to go on the assumption that everybody can factor that. So what does that mean? It means that in this first example, 2a plus 1 equals 0, and a minus 1 equals 0. So a equals negative 1/2, and a equals 1. Now, were we done this example? Well, no, because it wasn't A. A was an invention in our mind to make things easier to understand. A was sine of x, so what we really have is this. And now we are solving an equation that we learned how to solve yesterday. We can find a reference angle. We can locate which quadrants the terminal arm can lie in, and then we can determine the rotation angles. What do we want here? We want 0 to 2 pi. Now, by the way, how many of you do recognize these as numbers that would be on the unit circle for y? See, this is the beautiful thing about the unit circle is I can identify very quickly that this is one of the locations. Now, we have to grapple with something. This x here in sine of x is not x on the unit circle. This x is a rotation angle. Sine is the y coordinate, so y is equal to 1 there. Where is y negative a half? Here and here. I know the three locations without having to use my calculator. But if you can find those three locations without your calculator, then it should be no problem for you to follow along on your calculator as well. I would like everybody to find a reference angle for x if sine of x is negative 1/2. Now we want exact values in radians. We want exact values in radians, but you're not going to recognize the radian measure. So you should put your calculator into degrees. You do not take the inverse sine of negative 1/2, you take the inverse sine of 1/2, and you will get a reference angle, correct me if I'm wrong, of 30 degrees. Well, that means the reference angle is pi over 6 rads. So now this is good practice for what we were talking about just before we started this lesson. Which two quadrants are we going to be drawing this reference angle of pi over 6 in? Well, sine of the angle is negative. Now we go to our knowledge about how to calculate sine. Sine is y over r. So where is y negative? It's negative below the x-axis in quadrant 3 and 4. Make sense? So we have to draw this reference angle in quadrant 3. This is pi over 6. And in quadrant 4, this is pi over 6. So now we can list the solutions. The solutions are what's indicated by the red here. That's theta, the rotation angle. And this one, that's theta. Once again, theta has a direction to it. It's got an arrowhead on the end of the arc. The reference angle is just an angle. I really hope that determining that the first one in quadrant 3 is 7 pi over 6 and the one in quadrant 4 is 11 pi over 6 is kind of simple, doable. I'm counting off in my head pi over 6s. I would just show you with my arms, but I'm recording this as well. This is 0, so there's 1, 2, 3, 4, 5, 6, 7 pi over 6. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pi over 6. Now we run into a bit of a bump in the road. I want you to find the reference angle for this trigonometric equation. It's 90 degrees, isn't it? In which quadrants, this is where we're going to have a bit of a problem. In which quadrants is sine positive? Here, right? So I'm going to draw a reference angle of 90 degrees in quadrant 1. I'm going to draw a reference angle of 90 degrees in quadrant 2. But they end up being in the same place, don't they? They end up being on the positive y-axis. So I'm going to write pi over 2 because we do want to work in radians. That means that this is the location. I don't care whether you call this the reference angle of pi over 2 or this the reference angle of pi over 2. The simple fact of the matter is the rotation angle is pi over 2. So these are thetas that I have written at the bottom. Theta equals 7 pi over 6, comma, 11 pi over 6, comma, pi over 2. Any questions with that example? You will notice that I pinpointed those three locations just with my knowledge of the unit circle though, right? I drew the circle and I said, well, sine is negative a half here and here, sine is 1 here. Let's try one more. Well, let's try a few more, but the next one, write a general solution to that equation. Well, we could write this. 7 pi over 6 plus multiples of 2 pi, 11 pi over 6 plus multiples of 2 pi, pi over 2 plus multiples of 2 pi. Of course, n is an element of the integers because that's positive and negative whole numbers, including 0. That means we can add or subtract that multiple of 2 pi. We're not quite done with this one because there is a tidier way to write the general solution. And you have to visually see these three solutions or these three locations are all the same angle away from each other. It's called the Hippie equation because it forms a peace sign. Just kidding, but we don't call it that. All of these angles are 120 degrees away from each other. There's nothing wrong with saying this. But what you could say instead is that theta equals pi over 2 plus multiples of 120 degrees. And that covers all three situations. Students will often ask now, okay, so which is right? And I'm telling you, they're both right. And I've even seen on a diploma exam questions like, write your solution in 2 different ways. Or on a multiple choice, Sandy writes this for a solution, and Kelly writes this for a solution. Who's right? They're both wrong. Kelly's right, Sandy's wrong, etc. They're both right. So you should understand that they are equivalent. All right, let's take a look at the next one. Solve secant squared x minus 2 equals 0. Oh, okay, well, just a second. Is it quadratic? Yep. Secant squared of x means secant of x quantity squared. So what this really is like a squared minus 2 equals 0. I tend to use the letter a. And what I've done is I've taken secant of x and I've changed it to a. That's what I'm doing. I'm turning this into a more familiar looking thing. Many of you don't need to do that. And I will show you what to do if you don't want to. So this is quadratic, but there's no linear term. I just dive right in. I rearrange for a squared by adding 2 to both sides. I take the square root. So a is plus or minus root 2. That's where we are at. Then we come back to reality. It's not a, it's secant of x. So we have now secant of x equals root 2, and secant of x equals negative root 2. How many of you, by the way, could handle just doing this? You don't have to literally on paper change the trigonometric ratio to some other letter. You could do it that way. Anyway, we have a little bit of prep work to do here before we can find a reference angle. It is to write cosine of x is the reciprocal of that, because, am I right? Secant and cosine are reciprocals of each other? Pretty sure. And over here, cosine of x equals -1 over root 2. Just give some thought to this statement I'm going to say right now. The reference angle for each of these will be the same. If you want to use your calculator to find a reference angle here, you're going to take the inverse cosine of 1 over root 2. If you want to use your calculator to find the reference angle here, you're going to go inverse cosine of 1 over root 2. How many of you, though, recognize that 1 over root 2 is on the unit circle? It's the 45-degree marks, right? So what you could do is say, so I'm bypassing the calculator right now, then we'll do the calculator. You could say that if cosine is positive 1 over root 2, then it is in quadrant 1 or quadrant 4. If cosine is negative 1 over root 2, it's in quadrant 3, 3 down here and 2 up there. But where is the x-coordinate 1 over root 2? It is at the 45-degree angle. If you know your unit circle. So just by a show of hands here, how many of you are kind of with me on this? That you're getting to do problems in that way. I think it's a beautiful thing in terms of making your job easier. If you recognize these numbers, right away, you've got pi over 4. You've got 1, 2, 3, 4, 5, 6, 7 pi over 4. You have 1, 2, 3 pi over 4. All of these angles I'm writing down are solutions. And this would be 1, 2, 3, 4, 5 pi over 4. Were we asked to do this in degrees? Yeah. I like radians better. To me, it's easier. I don't have to add or subtract numbers. So I'll write the answers in green, 45 degrees. 315 degrees. Help me out on my math here, my numerical math. 315? Pretty sure. 360 minus 45. 180 minus 45 is, I think, 135 degrees. Yes? And this would be 225 degrees, 180 plus 45. I'm not going to do it with the calculator. I will just say, if you use your calculator to find a reference angle, you're going to get a 45-degree reference angle. So then you have to draw it in quadrant 2 and 3 when cos is negative, and in quadrants 1 and 4 when cos is positive. Were we asked to find a general solution there? Also state the general solution. So you know what we could do? And I don't want to do this. We could write 45 degrees plus multiples of 360. 315 degrees plus multiple of 360. 135 plus multiples of 360. 225 plus multiples of 360. How many of you see, though? It's a little tougher to see. That you can add multiples of 90. You put all 4 of those things on the same diagram. These two are exactly opposite each other. These two are exactly opposite each other. And that's a 90-degree angle. So what would happen here is on an exam, you might see a multiple choice question. You might do all this work to get these 4 angles, but they have it nicely packed into one succinct, easy to understand statement. All right, let's try number 3. Tan squared x minus 5 tan x plus 4 equals 0. We want to solve that in radians in decimal form, which means we're not going to put our calculator into degrees to recognize the angle because we don't care. It's decimal form. We need to factor this first. I am going to change this to a squared minus 5a plus 4. This is a quadratic equation of what I call a simple form, type 1, whatever your teacher called it. The important thing to recognize is the coefficient of the first term is 1. The quadratic term has a coefficient of 1. So it's not even trial and error here. If the first term has a coefficient of 1, you know that you need your two variables in these places, and then you have to find two numbers that multiply, in this case, to give 4 and add to give negative 5. Yeah? Which means a equals 1, a equals 4, but wait, it's not a, it's tangent. Tangent of the rotation angle equals 1. Again, the x here is what you often see in your trig equations, but it's not x on the unit circle. It's actually a theta. And tan of x equals 4. Both of these have positive tangents. I want everybody just to think about which quadrants tangent will be positive in. Tangent is y over x. Right? 1 and 3. 1 because x and y are both positive, so when you divide y by x, you get a positive tan. 3 because x and y are both negative. So what's the reference angle? X reference. By the way, you should know the reference angle for tan of x equals 1 is 45 degrees. But we want them in decimal form in radians, so you put your calculator in radian mode. You take the inverse tan of 1 and get 0.7. I couldn't tell you. Ryan, you got a nice loud voice today. Can you tell me what you get when you go inverse tan of 1 in radian mode?
You get 0.785.
So I'm going to say 0.79. That's rads. And Ryan, I'm just going to stick with you because, again, I can hear your voice nice and clearly. Can you figure out a reference angle for the second equation?
1.325.
So I'm going to say 1.33 rads. We draw for the first equation that reference angle in quadrant 1 and that reference angle in quadrant 3 because that's where tangent is positive. For the second equation, we draw 1.33 in quadrant 1 and 1.33 in quadrant 3 again because tangent was positive. And then it's a matter of figuring out the rotation angles, which I'm going to indicate with a green arc. Theta is equal to 0.79. We need to take for this second one, this is what I'm pointing at for you video watchers, we need to take pi plus 0.79. You need to take 3.14 plus 0.79 and get 3.93. Is that right, Liam? Okay, so 3.93. You get that? Oh, sorry. Pi plus 0.79. And the reason for that, Jason, is that from here to here is pi. So then we have to add that extra 0.79. Does that make sense? Over here in quadrant 1, it's just 1.33. And then the same idea that we did for the second one, the 3.93 that we got, we're going to do here. That from here to here is pi, and then we have to add the 1.33. So we should get 4.47. I really think you get the idea, but let's just do one last quick one to cover all the bases, because in this case, we have a quadratic trigonometric equation, but there's no constant term. So we still zero it. We still write 3 sine squared x plus 2 sine x. This is equal to 0. So now I have to tell you, this crutch that we lean on to change everything to a, we have to work away from that. So could you solve this equation by saying 3a squared plus 2a equals 0? Yes. But you should be able to factor that original equation. There's a common factor of sine of x. Sine squared of x means sine of x squared. So I can factor a sine of x out of this and be left with 3 times sine of x plus 2. And I'm telling you that sooner or later you have to go away from changing everything to a or some other letter in the next unit. This becomes sine of x equals 0. This becomes sine of x equals negative 2/3. I seem to recall seeing degrees up top. Tell you what I'm going to do. I'm going to solve the remainder of this with my graphing calculator and not really write much. By the way, sine of x equals 0 is here and here, because on the unit circle, the y coordinate is 0 there and there. Okay. We need to be very careful here in looking at the domain. Do we include 0? Yes. Do we include 360? No. So one of our solutions is 0 degrees for this statement and 180 degrees. If you're not a unit circle kind of person, humor me and find the reference angle here. Take the inverse sine of 0 in degree mode. Not that it really matters, but it's 0, don't you? Yeah. So now this is awkward because our whole 2-quadrant things just falls to pieces here, because 0 is not positive nor negative. But it doesn't matter which quadrant you put a reference angle of 0 in. Quadrant 1, it lands here. Quadrant 2, it lands here. Quadrant 3, it lands here. Quadrant 4, it lands here. So it's 0 and 180. I'm going to find the reference angle for my second one. Make sure I'm in degree mode. And take the inverse sine of 2/3. 40, I'll just say 42 degrees. I don't care about the rounding. In which 2 quadrants am I interested in? Sine is negative down here where y is negative. So I will draw this. One of them will be 41 degrees here. One of them will be 41 degrees here. You need to figure out what this angle and this angle are. How's my subtraction here? Is it 319? Is that? And so this one here would be 360 minus the 41. This is 180 plus the 41. It's very sequential, consecutive learning here. What you learned yesterday was solving a basic trigonometric equation, now is included in solving these quadratic ones. So there's 2 problem sets in your textbook that you should practice with, and there are additional questions on the following page of the handout. Does anybody have any questions with regards to that last final example?